Well, welcome everybody to, this is probably what, the sixth Shale networking forum that we've held, and we have some really exciting results to talk about today. In particular, the Marcellus Shale Energy and Environment Laboratory. The wells were drilled just about, well, a little over a year ago, and completed and stimulated at about a year ago. And we now have a lot of results that have been coming in, and so you'll hear an update both on the project and some of the individual results. I'm Brian Anderson. If you don't know, I'm the director of the WVU Energy Institute and professor in chemical engineering, and I've been asked to give just a little bit of a update on some of the natural gas mountain of excellence work around the university, including upstream and downstream. You'll hear about the biggest project in the upstream area that we have going on, and another project also led by Professor and Chair of Geology and Geography Tim Carr is the International Forum on Unconventional Gas Sustainability and the Environment, or INFUSE for short. That project is funded by the Department of State, and next week we're hosting what will be our fifth cohort, is that right? Our fifth cohort on campus from South Africa to teach the international community how unconventional shales are developed in the United States, both from an environmental standpoint as well as technical and policy, regulatory, the whole kit and caboodle. And the South African delegation will be here the better part of next week. Other efforts in the natural gas mountain of excellence, natural gas focus area in the downstream area, as many of you have met Professor John Hu here in the audience, who is the director of the Natural Gas Utilization Center in the Statler College of Engineering. And John has really been hitting the ground running on a lot of different natural gas utilization efforts, including a national network of manufacturing institutes proposal that went in with the American Institute of Chemical Engineers a few months ago. We're in the review stage, and oral interviews have already happened, and we expect to hear about the outcome of that solicitation soon. The NNMIs are $70 million of Department of Energy funds, matched with approximately $140 million of cost share between the industry partners and academic partners. And this particular NNMI is focused on process intensification and modular processes, and WVU was a part of a center within that institute. That's WVU, the University of Pittsburgh, Gas Technology Institute, and the National Energy Technology Lab, specifically focused on modular technologies for natural gas utilization. And so it's really on topic, and we're really excited about that proposal. Earlier this summer, we found out that we were part of the successful team of another NNMI called CESMI, C-E-S-M-I-I, which is in smart manufacturing. And we are part of what's called the Gulf Coast Node, which is focused on petrochemicals and, in our particular case, natural gas utilization, go figure. And in fact, these two NNMIs, we're working on how to interface them together. These efforts are also part of an alliance that we joined with WVU, Pitt, or the University of Pittsburgh, Carnegie Mellon University, and Case Western Reserve University, called the Tri-State University Energy Alliance. And one of the major pillars and focus areas of the Tri-State University Alliance, or TRUE Alliance, T-R-U-E, is in natural gas utilization. So again, go figure, we're trying to leverage this resource that we have in the region to build up a manufacturing industry across the tri-state region. And the Tri-State University Energy Alliance and what was the Tri-State Governor's Agreement is the effort to put together West Virginia, Pennsylvania, and Ohio resources into one pool and act as a tri-state, superstate region in 4 different areas of focus: infrastructure and transportation. And we have a transportation and infrastructure meeting tomorrow in Pittsburgh to work on what some of the necessary infrastructure needs are and critical infrastructure needs are for this region. as well as in the other 3 areas of focus in that tri-state agreement are workforce development, research, and marketing and promotion. In this transportation and infrastructure group, one of the key projects that has spun out over the last year is led by Doug Patchen here in the room, called the Appalachian Storage Hub, or Appalachian Storage Study, for the storage of natural gas liquids. As you'll hear about in the Marcellus Shale Energy and Environment Laboratory, it was a dry gas well, but many of the wells in the Marcellus and Utica have significant liquids: ethane, propane, butane, and other natural gas liquids. And we've identified one of the critical needs in order to push forward the downstream development of the petrochemical industry is the development of a natural gas liquids trading point in this region, similar to Mont Belvieu in Texas, and the associated infrastructure that includes natural gas storage, or natural gas liquid storage in the region. And so Doug is working with the 3 geologic surveys of, again, West Virginia, Pennsylvania, and Ohio to identify potential locations for natural gas liquid storage. And then we're in other efforts in the transportation and infrastructure subgroup working on the necessary pipeline, fractionation, and infrastructure that would be associated with a true storage and trading hub for natural gas liquids in the region, all related to the development of the crackers, the ethane cracker that was recently announced by Shell, the final investment decision of a $6.2 billion cracker facility in Monaca, Pennsylvania, and the hope that companies like PTT Global Chemical will follow suit with their final investment decisions early next year, and they will need such infrastructure to support those cracker facilities. As a note, the Shell cracker will take about 105,000 barrels a day of ethane. The PTT Global is on the order of 65,000 barrels a day of ethane. And there are lots of other opportunities in that petrochemical industry. So we in this region don't want all of our ethane to be shipped to Philadelphia or Texas. So we want to use it here. So that's the crux of a lot of the effort going on around campus in both the upstream and downstream areas. You'll hear quite a bit more detail about the MSEEL project today, so I thank you all for being here. I'll introduce Professor Tim Carr. Dr. Carr is the chair of geology and geography in the Eberly College of Arts and Sciences, as well as the Marshall Miller energy professor also in that department, and the principal investigator on the Marcellus Shale Energy Environment Laboratory, Infuse, and a number of other projects. Tim spent most of his career in industry, and we were lucky to grab him and steal him from Kansas, and so we're really happy to have Tim here and lucky to have Tim here. So I'd like to hand it over to him. I have a student's thesis defense to get to today, so unfortunately I won't be able to stick around for the whole time, but you're in good hands with Tim.
Okay. Well, thank you, Brian. Oh, yeah, I came the same year Huggins came from Kansas. We were a package deal, but he got more money than I got. And he lives right around the corner from me. I'm not supposed to talk very long, so I'll just quick. We had MSEEL review meeting. We had 70 people here last week, a number of people from Ohio State, and I see a couple back here. And then went through, spent good all afternoon, from 1 o'clock till 6 o'clock going through that. But there's the MSEEL site there on the picture, and that was when it was being drilled. And it is a long-term collaborative field site. And it's going on things are going on right now. A lot more will be going on this winter. We will be doing production logging this winter. Those 2 wells are choked back to 20% and supply the whole city of Morgantown. So I always give a new meaning to buy local. Anyway, and that's what it looked like when they were fracture stimulating it. And you can see all the Schlumberger trucks out there. And it's a very cooperative project. We had people from a number of institutions, and also from DOE, and also from the national labs. They were here last week. So that's really all I have to say about it. There's a lot going on. And Dr. Weisel came to us, 4 or 5 years ago, I guess, something like that? 6, oh boy. From the University of Alabama. And she's a sedimentologist in the Department of Geology. And I'll just give it to Dr. Weisel.
Welcome, everybody. My name is Amy Weislow. I'm in the Department of Geology and Geography, like Tim said. And I'm going to talk to you today about some work we've done on samples acquired from the MSEEL project. And I'd just like to acknowledge the collaborators in the Geology and Geography Department, Dr. Shika Sharma, Dr. Joe Donovan, and my master's student, Brittany Hupp, who has done a lot of the groundwork on this project so far. And also would like to acknowledge Tom Wilson, and Tom Peronish for their contributions to the MSEEL project that have been helpful as we're navigating through this work. We've done some of this work in cooperation with folks from the shared research facilities, Marcela Rodegalo and Wei Chiang Ding, who have helped us with the use of their facilities. I'm presenting some data from ACT Labs, which was done in cooperation with Yakov Kautsta. And also Louis McDonald and Heather Watson in the Davis College helped us as well. So the samples have come from MSEEL. The analyses were conducted through MSEEL support, as well as a faculty research grant that I was awarded and student grants to my master's student, Brittany. So you guys are probably well aware of this, but I want to orient ourselves with the rock units here, because most people are very familiar with the Marcellus Shale. It's the famous unit, and its overlying sort of accomplice, the Mahantango Formation, doesn't get a lot of attention, primarily because it lacks the organic rich facies. So we have this Marcellus Shale unit on the bottom, ranges around 100 feet thick typically, it has that organic rich facies. But as we move upward into the overlying Mahantango Formation, we lose that organic matter and we get more of a clay-rich shale deposit. So our interests lie in examining the difference between these two and trying to figure out what really changed. So the Devonian time, if we kind of take a step back, travel back in history, here's West Virginia, located in this map right here, and this is what we would have seen if we could go back to the time when the Marcellus Shale was being deposited. Large kind of inland sea, very shallow. And if you could see on the adjacent diagram, which isn't showing up too well on this screen, but there's essentially within this circle, so there's Pennsylvania and then West Virginia just to the south, there's these clastic wedges that formed. And essentially these are just sediment that is eroded from the highlands and then transported into this inland sea and deposits just along this coastline that was present in sort of central West Virginia at that time. So in foreland basin systems, the clastic wedges typically thicken towards the highlands and then thin away. And as you move away from the sort of mountain belt that's growing, you get a decrease in sand and clay shed from that mountain, and you tend to get a more abundant organic matter preserved. And that's essentially where the site of the MSEEL drill hole would be sort of beyond that influence of that sandy and clay-rich clastic wedge out into where the organic matter was forming. So there's some competing processes that interact, and from a geological perspective, we're trying to understand how these processes compete and ultimately result in the organic rich facies of the Marcellus Shale, and then also understand what changed to produce the clay-rich Mahantango Formation. So there's kind of three key factors, which is, first we have to have microbes making the organic matter, and those microbes need to eat, so we need some food being delivered to the basin as well. We also have clay that can be added to the basin that will dilute that organic matter. So to get a nice unconventional shale reservoir, we want to keep the clay out. And then we also need to preserve that organic matter. So if the water column is oxygenated throughout that organic matter, even though the microbes are doing their job and creating their organic matter, it won't be preserved in the rock record. It'll be oxidized down at the bottom of the sea, and it will be lost as a resource. So what changed? We have this Marcellus Shale, and the log is sort of shown here on the right-hand side. And at the base, we see the organic rich facies shown in bright red. And then as you move upward in the Mahantango formation, you see the cooler colors of the blue representing the clay-rich part of the column. So this was the well log taken from the MSEEL well. And we want to understand if generally what caused this change. Was it a change in biological productivity? Did the microbes just stop? Did they not have enough to eat, essentially, or to metabolize? And we can look at that through examining stable isotope fractionation that primary producers, the microbes themselves, produce or impart on the deposits. And that's work that Shika Sharma has been working on. The change in bottom water oxygenation can also be examined through redox indicators preserved in the deposits. And Shika's group is also doing, as well as other people are doing some work on that. But we want to address kind of that last bullet, which is, did the actual amount of clay coming into the basin change? So we can do this in a few different ways. We can actually just have the rivers deliver more clay. We can generate more clay on land. So if the land is experiencing intense weathering conditions, that might increase the amount of clay that's available, and then we see that increases in the basin as well. Or we could lower sea level, which essentially moves the shoreline closer to the interior of the basin and it makes it a shorter transport distance for the clay to get out to the MSEEL site. So, or some combination of these. So what we have to work with are about 60 samples taken from sidewall plugs of the MSEEL well, and they're at about 2-foot interval, and then into the bottom, just the bottom bit of the Mahantango. And we've done a bunch of different work. I'm not going to talk about all of it. We've looked at the samples in a variety of different ways. And I'm going to show you sort of these last three, the mineralogy, a little bit of the elemental composition through XRF, and then some ages that we got through samarium neodymium isotopic dating. So just to sort of show you a big messy plot, these are all the samples that we analyzed through using the XRD and shared research facilities, and that basically allows us to see the phases of minerals, so what kind of mineral grains are present in the rock, and essentially excludes any organic matter. It's kind of blind to the organic matter. So if we just look at the bits of rock, essentially, that are incorporated in the MSEEL samples, we have the Mahantango samples off to the left, and then as you work your way to the right, you're getting deeper and deeper into the well, into the Marcellus shale facies. And you can see that it's pretty consistent, lots of mineral called muscovite, illite, quartz, and there does seem to be some sort of oscillation in the relative abundance of these minerals. But overall, it doesn't, the minerals don't really tell us a lot about potentially a change in source of clay. It seems like whatever was contributing clay to the MSEEL site over time was about the same throughout its depositional history. We also looked at some handheld XRF data on the samples, and these curves are shown here. And basically all this really shows is that as you move upward through the column, we see an increase in things like aluminum and titanium, and these are elements that are commonly found in clay. So we say, okay, that makes sense. We see the clay-rich signature in the rocks, and basically the XRF tells us the same. So we know that as the organic matter becomes lower in abundance, the clay basically becomes greater in abundance, and that's pretty much a standard thing that's been known for a long time. But then what we did was, where you see these triangles, we took 4 samples and had them analyzed for samarium and neodymium isotopes. So samarium is the parent element, it decays to neodymium, and the U.S. continent is kind of well known in terms of the rocks that form the U.S. and what their samarium neodymium age would be. And I didn't need to get into too much of the detail, but there's a map out there that says, okay, if you grab a rock from, say, up in Canada, that samarium neodymium age is going to be quite old, over 2.5 billion years old. That's in contrast to the bulk of the rocks that form the eastern U.S., which formed during, it's called the Grenville. And these rocks are much younger. They're only, 1 billion plus or minus a couple hundred million. But relatively speaking, that's a very big difference in age. So we analyzed our samples, and unfortunately, the one that was right in the Marcellus, oops, let me kick this off, did not produce any, I think I turned this off back, oh, there it goes, did not yield a usable result. But something interesting came back when we got the other results, and they're shown here at different sample depths. And what I really want to focus on is that 1.8, 1.7, 1.8 column off to the right. That's the age of the clay minerals, essentially, that they record from the rocks that were eroded to produce those clay minerals. And this is a lot older than any rocks in this area. If you drive generally in the eastern U.S., you're going to be on this Grenville region that doesn't get much older than 1.0 to 1.3 billion years old. So if we need to find a source of sediment that's older than this, we have to go somewhere to the north in the Superior Craton, or perhaps kind of somewhat to the east. This little black belt that swings through here is also about 1.8. And so what we think is happening is that we're interpreting a source of sediment to the north, picking up this very old Superior Craton rock, and then mixing it with this younger Grenville age, and then getting sort of a blended 1.8. So it's not quite as old as the Superior Craton. It's not quite as young as the Grenville. It's actually a mixture of those two. And it turns out that when you look at the very first picture I showed of the sort of Devonian time period back in the day, there's this little embayment that stretches up to New York and a little river that comes down that has been called the Paleo-Ontario River. So it seems that this river was the source of the clay minerals that we find in the MSEEL core. So this is kind of a little bit different way of thinking about sediment deposition in this basin. There's long been sort of an understanding of how the wedge has formed, with the source area being thicker, or with the sediment being thicker towards the mountainous area in the east and thinning towards the west. And we've often kind of tried to understand the distribution of organic matter. I keep turning this off. With that in mind, sort of comparing these west or east to west transects and trying to model how organic matter productivity and preservation would vary across a east to west transect. But it seems that we might need a better understanding of the north to south variations. And if you look at sort of this map that Tim and his student put together, there's these two sort of highly prospective areas in the Marcellus, to the northeastern part of Pennsylvania and then southwestern PA and northern West Virginia. And it seems that perhaps if we think about clay sort of marching down from Canada and filling in this basin, there's probably a significant difference in the depositional history between that northeastern Pennsylvania region and the Virginia southwest PA region. Maybe different age of organic matter deposition and maybe different duration of organic matter accumulation. So I'd just like to summarize the points here that I've made is that we've kind of used the MSEEL as an opportunity to look at change in sediment source through time, particularly the clay matter, and we seem to have nailed a pretty good record of influx from the north. And so we kind of then have a model where a river is bringing in all of the food for the microbes to produce the organic matter, as well as the clay. And during the development of the organic Marcellus shale in West Virginia, that clay was being sequestered up to the north. It was falling out of suspension, and just the nutrients were basically coming in to this part of the basin. But over time, as the basin kind of filled up, it could have been helped by a lowering in sea level, but eventually that clay made its way into north central West Virginia and shut down that organic matter productivity. So we think that if we can find or test these ideas by comparing the clay ages essentially around the basin, we might be able to better understand where the clay came from and then better understand why we find organic matter in the Marcellus where we do across the basin. So we're going to try to expand this work by sampling through the Mahantango. Oops. There's a well that's been looked at, the Marcellus. Part of this West Virginia 6 core has been studied by Shika Sharma and her students. We're going to keep going up to the Mahantango to see if we can expand this model a little bit through testing those samples as well. So thank you guys for your attention.
Thank you. Thank you, Amy. Our next talk is by Dr. Paul Zimkevich, who's the director of the West Virginia Water Research Institute. And Paul's been intimately involved with the MSEEL project. And one of our problems that I have out there is we're not producing a whole lot of water, so I actually have people fighting about flowback water. And I'll have to start selling it here.
This is a sore point of sort of management on my part of my technical field staff, and I have told them, I don't care if you stay there for a week, I want a 5-gallon bucket of that stuff. Don't come back and give me a hole in my data set. It drives me nuts. So yes, that is an issue because it's torqued on and off at various times. So what I'll talk about today is sort of a summary of what we found out in the first year of sampling on water and also solid waste. Part of MSEEL, as Tim has described. We're taking our chemical characterization samples upstream of the oil gas water separator. So this essentially is water directly out of the wellhead through a relatively short tube directly to this separator here. Well, the separator is not in a box like they usually are, but you get the idea. But the raw water comes in at one end and then comes out separated into the 3 fractions on the other end. But we get it before the organics are separated out or the gas is separated out, for that matter. So we're mainly focused on looking at organic compounds, BTEXs particularly, benzene, toluene, ethylbenzene, and xylene. Also radioactivity, mainly looking at the 2 radium isotopes, plus alpha and beta radiation. And we're also looking at the major inorganic ions. So I'll be talking about all 3 at various times here. We've sampled produced water, also flowback water, also injected water. So you have 3 kinds of water going into these wells. The first is first water going into the well is the completion water, or what's often called frac water. This is actually the hydraulic fracturing fluid. So that goes into the hole with sand, causes the fractures to occur, and then that comes back initially as is called flowback water, until the point where the company switches over from just removing that water from the wellhead to the point where they're producing gas. At the point where they're producing gas, then that same water stream turns into produced water. Now the volumes change pretty dramatically through that cycle, and so does the chemistry. And what we have found is that the nicest water on the site is the water that initially comes back up out of the hole, the flowback water. It's the least concentrated in just about everything. And it's mainly river water in this case, and you'll see some graphs that show what it looks like. And then is the water stays in the hole longer, and you start getting formational fluids mixing and coming back up. Concentrations of almost everything start climbing pretty dramatically. The neat thing about MSEEL is that most studies on produced water have only dealt with the first 45 to 60 days of flowback in produced water. Here we have, because we have the 2 wells that were drilled almost 4.85 years ago now, the 4H and 6H wells, we have 1,773 days worth of flowback data. So we have an idea what that water looks like. And then on the current wells, 3H and 5H, we have not only the production rates of water, but we also have the chemistry through that cycle, which is now out at 251 days as of our last sample, and we're continuing to sample every month, so we're extending that period. So it's way beyond where if you go look in the literature, you're able to find actual produced water and figure out what that cycle is doing, because almost all of everything we did prior to MSEEL basically just had salts going up like this, and they're still in the increasing phase in the first 45, 50 days. And so now we're starting to see some trends where it's leveling out. Another nice thing about MSEEL is that the company has given us access to their SCADA system, and their SCADA system is basically their system control, design, and whatever, their data collection system for gas and water coming out of the well. So we actually have that data on a daily basis. So we are actually able to collect what the water-gas ratios are, for instance. So we know how much water you're producing per cubic meter of gas production. And that's really important, because if you try to find out, and this is something I've been trying to get my hands on since about 2009, you're trying to find out on a basin-wide basis, what kind of produced water volumes are you actually getting in these things? Because I'm always trying to do a mass balance, like any ecologist by training. Well, if you try to do that just based on reported water volumes, you're not going to have much luck, because no one's compelled to report their water volumes. The state agencies generally don't require that. You get it on a sort of hit and miss basis. But here we're getting it from a particular well, a couple of wells, and we're able to, in this case, 4 wells. So we've got this 5-year cycle now, and we've got the 251-day cycles. And these are the results of both of those. So the reason this is an important correlation is that you have really good data on gas production, because that relates to royalties and it's regulated and all that good stuff. So we have a good idea what the gas production is. So we can then take those rates. In this case, I'm showing you cubic meters of water per cubic meters of gas, cubic meter of gas. And you can see the dynamics on the well on the left. That's 3H and 5H. Those are the younger wells. And then on the right, that's the 4.85-year-old data set from the 2011 wells. And you can see on the early stages, you have this decline in the rate. So you're getting more gas, less water through time. The average value in the older wells is about 2.4. You can see this better than I can. I'm trying to read off the screen. About 2.4 times, the ratio is 2.4 times 10 to the negative 5 cubic meters to cubic meters. And then and that blue line, by the way, is the average value. And then on the right, 4H, 6H, it gets down to about 2.36 times 10 to the negative 5 is the ratio. So again, on a baseline basis, you can then figure out how much water is actually being produced based on historical gas production rates. So this is really important data that you just otherwise wouldn't have access to. And the only difference between the one on the left and the one on the right, really, they pretty much, their y-intercept is about the same location. The slope of the curve is about the same. It's just that you have a lot more history off on the point of the curve where it starts going asymptotic. So these are the older wells, the 2011 wells, 4H and 6H. And on the left, the orange, is the actual produced water volume. And I've got these in cubic meters per day, and a cubic meter is 6.3 barrels. You know, oil and gas industry likes barrels. Scientists like cubic meters. Go figure. And the line down at the bottom, the blue line, horizontal line, is the average value for that. And the mean is about 1. As you go asymptotic out there, it gets to be about 1 cubic meter per day of produced water. The real steep part of that is the flowback cycle. Remember, I was talking about the flowback water that comes back before you start producing. And that's kind of interesting, because when we started studying wells back in 2008 or, no, sorry, 9 or 10, the flowback cycle on almost all wells in West Virginia, correct me if I'm wrong, Doug, was something like 4 to 6 weeks before they started producing gas. And so you had this really long cycle where you're just trying to get as much water out of the well as possible before producing gas. And in this case, we're down to a matter of days before you switched over from flowback to produced water. So that distinction is kind of becoming subjective over time. But you can see it's very high initially. So you're getting up in the 25 cubic meters per day of water production initially, and then that drops off to a much lower number. On the right, that's the cumulative curve for the same set of wells. And you can see what happens is, in these wells have not operated continuously. Tim pointed out that these are servicing the Morgantown market. So they vary with seasonality, gas demand in the Morgantown market. So you get periods of time. That's why these are not continuous, smooth curves. Although there's a pretty good R-square on this thing. You see that? Oh, that's a really, actually very good R-square. But nevertheless, you get these little bumps in the production line, and that reflects seasonality and demand. And you can also see where when the two newer wells came in, they shut these off for a while. So you had a flattening out of the curve. So don't read that as a zero production line. That's just you have a lot of zeros there just because there was no gas production. No gas production equals no water production. But nevertheless, with winter coming on, they are starting to produce water again from these older wells. So we're going to see that tick up a little bit, but it won't be huge. But you can see that cumulative line with all those qualifications starts looking fairly predictable. And you get to the point where you're producing water at a very sort of stable rate, about 6 barrels per day or a cubic meter per day. And that just seems to go on almost indefinitely, as long as you're producing. So this is the evolution of produced water. And on the left is the makeup water, which looks almost identical to the initially injected water, because the hydraulic fracturing fluid is 99.5% chemically makeup water. And this water is coming from the Mon River. So they had to pump down the river. They pumped up to a holding basin up above the well itself that would hold the 4.5, 5 million gallons of water that were required for the fracs, and mixed about 0.5% additive in with that in addition to the sand. So basically the chemistry is the same. I could have showed you another pie chart, but it would have looked identical for the actual injected water. And then flowback day 0, and that's the first day of flowback. You can see that water really changes a lot. The makeup water, we monitor the Mon River every month, and we've been doing that for the last 6 years now. That is really typical Mon River water, mainly sulfate, calcium, some sodium, little stuff, but mainly a sodium, calcium, sulfate water. That's typical Mon River water. TDS is about 285 milligrams per liter, which drinking water standard for TDS is 500. So it's nice water. Once you get to flowback day 0, your TDS has already gone up to 27,800 milligrams per liter, which is way beyond the point where you want to drink it. And the chemistry has completely changed. There's no sulfate left in it to speak of. There wasn't much on a mass basis. Don't be completely fooled by that, because the concentration is just so much higher of other stuff. But the sulfate's pretty much out of the picture. And mainly what you have there is a sodium, calcium, chloride water with little bits of other stuff like strontium, barium, some alkalinity. And so if you look over to the right, that's flowback day 160. TDS has gone up to 121,000 milligrams per liter. And that's 12%, by the way. So if you had a liter of water, 12%, if you dried it down, 12% of that volume would be salt. I mean, dry salt. So that's a lot of water, a lot of salt in that water. But the concentration has gone way up. But the ionic ratios don't change a whole lot, except that you start seeing more things like barium and strontium showing up in the water. That's those little thicker wedges. So these are the results out to day 251 now for the same wells, 3H and 5H. And the graph on the left is the total dissolved solids in milligrams per liter. And 3H is the blue, and 5H is the red line. And you can see what's happening there. You can see the interruptions in production. So I'm running out of time, am I? Okay. Anyways, so the TDS seems to be going up, and it was looking like it was going asymptotic at about 120,000 milligrams per liter. And then they diverged on couple of samples, and so we're continuing to sample to see if those come back together or if that's a real trend or not. But it's interesting because they're managed very differently, and that may have something to do with the kind of water that you're getting back out of these. Now on the right, those two pie charts show the ionic ratios. These are not concentrations, but just ratios. So, and that's the ratio of all the ions to total dissolved solids. And that's what we look at when we're trying to describe the ionic composition or the sort of the chemical signature of the water. It hardly changes at all. The only difference between, and that the number on top of that's the 12 is flowback day 12. And then the 251 is day 251. Even though the concentration is going up from about 50,000 milligrams per liter up to 120,000 milligrams per liter, the ratios of ions don't change. So that suggests that you're really getting formation water that has a fairly fixed chemistry about it, and you're just basically losing by this time you've lost the injected water. It's out of the picture, and you're just getting formation water. And it's not like this is a wet formation. This is a very dry formation. And I've asked Tim, I've asked Doug where the water's coming from, and correct me if I'm wrong, but basically you have these little clay particles, and they have a little bit of water around them, and then hydrocarbon outside of that. And then each one of them is in these, you can pulverize this stuff and it looks like talcum powder, but yet nevertheless, they have this bound water around each one of the clay micelles. And that's probably the evaporated seawater that you originally found in the basin that Amy described that is just popping out now. So it's probably a signature of Devonian seawater. But anyways, you're not seeing changes in ionic composition at this point. Organics, these wells are in the dry part of the Marcellus Formation. There's not much in the way of organics. I illustrate toluene here. That's about as high as anything gets. Benzene is extremely low, mostly non-detects. Okay, and over to the right, you can see rads. And the rads are, one well keeps going up, and they get very high. They get 20,000 picocuries per liter. And the other one's down a much lower value than that. We also looked at green drilling muds, and that's what they used at these sites. We've looked at other sites in the past where they used conventional oil-based muds, and they've tripped the TCLP test every time. These don't. And so the conclusion we reached is that it's the drilling fluid itself, not the inherent formation, that's tripping the TCLP test. And that's for organics and inorganics. And then we also looked at radioactivity in the drill cuttings, and these are the results that we get. So we have the two radium isotopes. Potassium is up in the 20s and 30 range, but radium is generally a lot lower. You can see the combined never gets above 10. It's not trivial, but it's not really what you consider hot stuff. Thank you.
Okay, thank you, Paul. So our last talk here is Dr. Kasia Minian, and he's been looking at the flow through these rocks. It's quite amazing that these rocks do flow, because we're talking here in the nanodarcies and nanometers, so billions of a meter. So these are very, very tight rocks.
Okay, we're going to talk about some petrophysical characteristics of the shale here. Basically, whenever we look at any producing formation or a reservoir, we have to have what we call a network of connected pores. This would allow basically for the fluid to be able to flow through this rock, and also the spaces between these grains will provide the storage space for the fluid. Now, typically we use two parameters which reflect this ability. One is porosity, which reflects how much fluid we can store within the rock, and then the other one is permeability, which shows how easily the fluid will flow through the rock. Typically, when we measure the permeability, we take a sample of the rock, we call it a core plug. It's placed in a core holder, and we flow an inert gas through it, typically air or nitrogen in the laboratory. However, when we do this thing in the laboratory under low pressure conditions, we measure a permeability which is much higher than it is in the reservoir. The phenomena is referred to as a slippage. That means that within the pores, when we have low pressure, these gas molecules can flow freely without having to come into contact with the pore walls. But when you increase the pressure, compress this gas, and pack more gas molecules, they will come into contact and cause more friction. So you have a lower permeability at higher gas pressures, and we usually correcting it by application of this gas slippage method, which we plot the permeability versus inverse of the pressure and extrapolate it to infinite pressure over 0.1 over P. That gives us what we call the absolute permeability or liquid permeability. Now, when we measure the properties of the shale, we have to consider a number of different things that impacts our measurement. One of them is obviously the size of the pores. In typical conventional reservoirs, we're looking at the pore sizes or pore size diameters in the range of micrometer. But when we get to this unconventional shale reservoir, then the size of the pore would drop down to nanometer, and that would cause impact on the kind of flow regime that we have within these rocks. Another aspect is because the shale does contain organic material, it absorbs gas, and so we have to be aware of that. We've been doing our measurement, how much of absorption we'll have or how to account for that. Also, shale is known to have natural fractures associated with this, so we have a system which has two different porous media. One is the matrix of the rock, one is fracture. Also, we have gas which could be both in the matrix, could be also in the fractures, could also be attached to the surface of organic material. So these make it a little bit more challenging as far as the measurement because of ultra low permeability of the rock, the pore sizes are in nanometer. They're knowing the flow regime for slippage correction. Also, we want to conduct the experiments under, or determine the properties under reservoir condition, which is the impact of the stress and also the impact of the adsorption. Typically, it is not practical to do conventional measurement on the core samples because of extremely low permeability. So they have developed different techniques such as crush sample or pulse decay. I'm not going to go over detail of those things, but the problem with these techniques is that we don't have standard protocols how these tests are measured. You cannot apply the stress or pore pressure to these, most of this kind of measurement. The interpretation is very complex and sometimes. So what will happen is a lot of time when the companies send their sample to different laboratories, they get values for the porosity and permeability which are several order of magnitude different. So you really do not know how to interpret the information. So what we did a couple of years ago, we developed a laboratory setup with very extremely accurate pressure transducer and pressure differential measurement and fully automated system, so we can actually measure very extremely low volumes and small pressure changes, so we can determine the porosity and permeability of the shale. This we refer to as a petrophysical, precision petrophysical analysis, or PPAL, and we utilize this setup that we have to measure the porosity and permeability of the sample we obtained from the MSEEL site from the science well. We use both helium and nitrogen for permeability measurement. The first set of experiment we did, we increased the gas pore pressure to determine the effect of a slippage on the, and determine actually the absolute permeability. Also, we made number of different measurements of our different stress value by applying a different confining pressure to the sample to determine how does that affect it. One of the things which is very obviously we notice is, I have two charts in here. One shows the measured permeability as a function of traditional technique that we use slip flow, the slippage effect. And if we apply that one to our measurement, you notice that when we extrapolate it to 0, we get absolute permeability comes out to be a negative number. That is not uncommon because basically we're assuming the flow regime is a slip flow. That is true if you have pore sizes in micrometer. But when we get into nanometer, that assumption is not correct. Actually, we fall typically in what we call transitional flow. And in that case, you actually plot the measured values except over versus 1 over p squared. And if we do that, you notice that we get a consistent number like it's 124 nanodarcy for the permeability in this case. Now, that's what's with the helium. We did the same thing with nitrogen. And of course, in this case, there is some adsorption effect with nitrogen. So we increased, during our experiment, we stepwise increased the pressure and stepwise decreased the pressure. And the way we account for the adsorption, we allow the flow rate to stabilize. In other words, as you're increasing the pressure, the flow rate is slow and then it stabilizes, and when you go into the reverse. So when it stabilizes, that means we have reached equilibrium and there are no adsorption effect, and then we do our measurement based on that. This plot shows the measurement we did with nitrogen, both increasing and decreasing, and as you can see, there is some hysteresis here, which means that something happened to the sample. In fact, both of them give us the same absolute permeability, but this is lower than the one we measured with the helium. So nitrogen gets adsorbed to the sample, as we can see here, and that causes the hysteresis in our measurement. Also, it reduces the permeability. That is because when gas gets adsorbed, the rock will swell slightly, and it reduces the pore sizes even more, so it's going to reduce the permeability. Then we also made measurement against different stress. In other words, we maintain the pore pressure constant, increase the confining pressure, and this shows the reduction in the porosity of the sample against the stress, and this is the permeability. Actually, this permeability measurement are determined by measuring that multiple different pore pressure to estimate the absolute permeability. So you can see the absolute permeability is declining. Typically, when we plot this permeability versus stress plot, we get a straight line if we have a uniform rock. But as you can see, this is a very nonlinear behavior. In fact, we know it's a fractured formation, so what we did, we have a special way of plotting this thing referred to as Walsh plot that you can determine where the changes occur in the slope of the line. If you have multiple systems in here, you will get different lines, and every time one of these slope changes, that means one of those systems is closed up. So Basically, when we're at the lowest stress here, both matrix and fractures are open, but by the time we reach to this point, the fractures are closed and we're only producing from the matrix of the rock. That will give us a pressure around almost 4,700 psi stress, where the natural fractures are closed in the sample. So that's called the fracture closure pressure. So to summarize, we were able to measure the porosity and permeability of the shell in a wide range of pore and confining pressure. We determined that application of transitional flow correction provided accurate and consistent values for absolute permeability. Also, gas adsorption resulted in permeability hysteresis, which is related to pore size changes with the swelling of the rock. Now, of course, in this particular sample, we just used nitrogen, and the effect of adsorption was not huge, as you saw in the hysteresis. But we have done experiments with other samples with carbon dioxide, and you see a huge difference there is much wider hysteresis effect. But what will happen is because of CO2 swelling is significant, it completely deforms the sample. So we didn't want to deform the sample here. We didn't use the CO2 in this case. Now, of course, how much of swelling you have is a function of how much organic material we have and what kind of gas we use. Of course, as I said, with CO2 it would be much higher. As we noticed that we have a nonlinear behavior as regard to stress with the permeability and porosity, which represents fracture and matrix system, and we were able to determine the fracture closure pressure. And basically what we can see that 50% of total permeability we're measuring is coming from the fractures, and 12% of the porosity only comes from the fractures. Okay. All right, that concludes my presentation.
Thank all three presenters. And people may be wondering why we're worried about the permeability and the porosity and the water, but in a fundamental thing, we don't even know how much these wells are going to produce because we can't do a fluid flow simulation unless you know what things are going to flow. Any questions? Anybody? Yeah, Dr. Bajura.
Well, the concentrations of bromide are generally in the range of 500 to 1,500 milligrams per liter. So I'll leave that to, and the only other anion to speak of is chloride. And chloride overwhelmingly dominates the anion component, but the only other anion there is bromide. But those are the concentrations. Whether you can separate it from chloride efficiently, I don't know. But there's a lot of it. Oh, another thing I forgot to mention because Trina was tormenting me with my time.
That's her job.
But I meant to point out that the total rate of total amount of water that was returned after our longest observation period, and that was the 4H, 6H wells, was about 8%, which is consistent with a finding that downstream strategies generated a couple of years ago, looking at more basin-wide evidence. So 8% looks like the return rate. If you asked the literature, according to the literature 4 or 5 years ago, they would have said 20 to 30%. It's much, much lower than that.
Well, our experiment shows it does swell when we use the CO2 in the shale samples we had. Now it depends on how much organic content you have, but typically, yes, I would say it would swell and it would reduce the permeability to some degree. Now, that might be insignificant depending on, whether you want to open a fracture or not. If you're going to use the CO2 just for fracturing, it's as a fluid, it's a liquid CO2, it might not get adsorbed that quickly as opposed to a gas CO2, gas-phase CO2. There has been some studies being done on using CO2 as a carrying fluid and, mixing it with sand. I haven't seen anything has been done in the field with the shales, but they're trying, some laboratory experiments on that.
Well, okay, so there are a couple of fluids involved. One is your flow, and I think you're thinking of, there's drill cuttings, first of all. And the drill cuttings come back with the drilling mud in the drilling process. So that's where you get the coarser grained rock material, and that comes out as the drill cuttings. once you've completed the well and you start getting flow back and then produced water, the water comes out almost perfectly clear. And then almost immediately it starts oxidizing to ferric hydroxide. And there usually are a couple hundred milligrams per liter of ferrous iron coming out of the hole. So the only solids that you get really are the precipitation of the ferric hydroxide. And again, that's a very quick process at that pH once it oxidizes at the surface. You also get some precipitation of sulfates, barium and strontium will scavenge any sulfate that's left in the water. So that constitutes what we call sludges, tank bottoms, and that also pulls down the radioactivity. So the radioactivity drops out as a sulfate as well, the radium does. So those tank bottoms are the only place you see a concentration of bad actors. Otherwise, the fluids that pass through and go to recycle are usually field filtered with either plate and frame presses or just allowed to settle out in impoundments. So, and the industry does not really want to see any particulates going back downhole again. So that's usually a very low suspended solids count by that time. I would be astonished if we found rare earths coming back in flowback water just because the pH is too high. They're just not soluble. They precipitate as hydroxides at about pH 4.5. And this stuff is always coming out of the ground at about 6.
Well, the clays are coming in through rivers, and the work that Shika Sharma has done and her students have shown that the microbes are munching on terrestrial-derived organic matter. So you have to bring that organic matter from land to feed the marine microbes that then produce the organic matter that becomes the reservoir and the source, the unconventional resource. So the clays are just sort of telling us where the rivers might be coming from and why the microbes are getting enough to eat that is basically they're being fed from terrestrial derived material, but yet the clays, when they're not there, we get the organic matter, facies preserved, but eventually they do come into the basin. So we're trying to figure out why they come into the basin and basically if there's a relationship between feeding the microbes, the clay influx, and then trying to basically get a picture of the aerial distribution of the organic matter. Tim and his students have done a lot of modeling to try to predict where, based on drilling records, where these hotspots are for productivity. And we kind of live right basically on one, but it's not, the Marcellus is not equally productive everywhere. And it probably has to do with how much food those microbial organisms are getting, and then how much dilution of the organic matter by clay coming in from rivers.
I want to thank the speakers and thank you all for coming.